Thank you. So first of all, let me thank the organizers for this nice workshop and to apologize for my very spotty participation. I will be trying to catch up with all the talks using the online material. I am on maternity leave, so that's why things might be a bit jumbled at the moment. So I'm going to launch straight into hydrogen storage and why I'm looking at it. I hope no one needs convincing that hydrogen could be a really useful fuel and it would be environmentally very helpful and net benefit. There's a major bottleneck when it comes to using hydrogen, and that is of storage. So we want to be able to store hydrogen using low volume and in a cost-efficient way. And at the moment, the typical ways of storing it are very expensive. So one alternative would be to store it in its molecular form, but to be able to release it as needed to a proton exchange membrane, for example, in a vehicle, right? We know that those function in the 3 to 100 bar pressure regime, and ideally we'll be able to do this on ambient temperatures. So my colleague Andrea had a look at looking at the partition function to be able to deduce what would be the binding energy range that would fit in those conditions of pressure and temperature. And so we had previously computed hydrogen on a carbon nanotube using quantum Monte Carlo, and he plugged that absorption energy into the partition function to come up with this figure. And you can see here that the sort of ideal regime that we're looking at binding a single hydrogen molecule in a material that might be a low dimensional carbon material is between sort of 200 and 400 millieV roughly. So that's quite you might say that's quite a weak energy range, but it's also actually very strong when it comes to hydrogen because it's a very small non-polar molecule that typically binds very weakly. And indeed, in the black line, you can see hydrogen on graphene. So that is plotted using the absorption energy that we computed using QMC for hydrogen on graphene, which you can see is far outside of the ideal regime, and it'll be too weak. So we're looking at how can we boost the absorption energy of hydrogen in the material. So one way is to go back to the beloved periodic table and think, how can I decorate graphene or such materials to make it lead to a larger absorption energy? And there are many works out there who have looked at that, who have done modeling to try and deduce what happens when you take graphene and you put a metal atom on it, how strongly or not strongly does it bind hydrogen? However, most of these works are done using, workhorse modeling methods. And then there's the issue that we don't really know how accurate they are and how predictive they are in their conclusions. So we would like to understand better the mechanisms, but also to be able to identify using QMC what are the promising materials. And so Andrea had initially used CP2K to do a quick screening by looking at group 1 and group 2 metal atoms by putting them on graphene and then just seeing from 1 to 7 hydrogen molecules, how strongly do they bind to that substrate. And so I'm not going to go into much detail with this complicated looking plot, but just to point out that 3 major mechanisms seem to emerge, or at least 3 major structures, and they're identifiable by the cross, the triangle, and the square. And the point is that those with a square structure tend to look like they might be in this ideal regime, which is illustrated by the yellow box. What does that actually mean in terms of the electronic structure? Why is this specific hydrogen bond-facing structure that looks at this metal atom in the center? Well, when we looked at it with more refined DFT using sort of more numerically converged settings and so on, we found that all those absorption energies actually shift up, unfortunately, away from the regime that we're targeting. However, then we're able to see that what the electronic structure is. And so here I'm showing you the density of states for calcium on graphene with 4 hydrogen molecules around it. And the key thing to note here is that typically calcium would have 2 valence electrons sitting in the S state, right? But actually what you see is that when you put it on graphene with the hydrogen molecules around, the D state of calcium, which is usually empty, becomes partially occupied. So you have some donation of its charge to graphene, so the whole system becomes metallic, but you still have some electron density left on the calcium. And interestingly, what happens is that that then spills into the antibonding orbital of the hydrogen molecules into the sigma star. And we can pick this up because when you look at the structure, you'll see that the hydrogen-hydrogen bond distance actually lengthens because the molecules are now more weakly bonded. However, the interaction with the central calcium atom is stronger. So this is a really interesting form of interaction. It's called Q-bus binding. And the reason it's particularly interesting is we can exploit this kind of sort of covalent interaction in different ways. One of them, for example, is if we were to apply an electric bias perpendicular to the substrate, you can see in the gray and the brown lines, what happens is that you can totally tune the absorption energy. And this is in the range of 50 to 100 millieV, let's say, which is really useful when we're talking about absorption problems. Whereas you wouldn't get that if you use a metal add atom such as potassium or sodium, where you don't have this Q-bus interaction going on. Okay, but one question is, are these absorption energies at all accurate? All of these energies I'm showing you are from PB plus D3. And secondly, is this actual Q-bus interaction itself viable? Now, there's a big but there because actually all the previous work has shown on the gas cluster, so without any graphene there, that the Q-bus interaction is largely overestimated in DFT. So I'm showing this work from Baidik et al., where you can see that in the sort of downward facing triangles, you have two wells, right? So you have the first well, which would be the Q-bus interaction of a calcium plus cation and hydrogen molecules. And the second one will be sort of maybe a physisorption well, so van der Waals interaction. And you can see that it's really indistinguishable between those two according to QMC. And they did that with B3 lip orbitals, but also, I believe, multi-determinant wave function as well. And so either way, it looks like this Q-bus interaction is largely overestimated according to other methods. So that got us thinking, well, what happens on graphene? Because as we all know, graphene is supposed to be special and it transforms our lives and so on. So we wanted to look at this with QMC for the larger system ourselves. So just to launch into a bit of the background, since it's a user's workshop, the setup you can see on the side, those are the systems we're looking at. We're talking about roughly 200 electrons, a little bit over, but in that regime per system. And we used the new GPU batched implementation, actually. We employed the determinant locality approximation, and the CC-ECP pseudopotentials are super useful for this work. Okay, and so then, oh, backwards. All right. So I just wanted to quickly mention some of the issues that we hit. One of them was really boring and plain. Basically, our wave function files using with all the K points that we needed for converging were a bit too big on Summit for some reason, and calculation just wouldn't move forward. It would crash. The wave function was too big. And we noticed that one of the issues is that because the wave function file contains all of the orbitals from all of the K points, that this individual file was too big, but if we were to split the files, then it would go forward fine. So in the end, that's what we did. So we figured, okay, we'll do an SEF calculation, then we'll do separate, non-self-consistent field calculations at each K point that we want to use. And then each QMC calculation is, of course, independent. But the point is that the wave function file that it was reading in was manageable on the machine setup that we were using. But then there's a question of which K points do we use? We have to make sure that the interaction energy is converged using that set and that everything matches up fine. So to do that, we actually ended up looking at the DFT band structure and the absorption energy at different K points to choose the most appropriate things. And one of the things we saw is that for 3 systems where there shouldn't be any Q-bus interaction, so that's the lithium, sodium, and potassium decorated graphene, we noticed that you get really fantastic convergence already at one twist. If you pick the right point, then basically if you use a converged K-point grid, as you see in the bottom of the table, versus just one point in the first 2 rows, then you're already within a couple of millieV, if not spot on. So that's fantastic. So that just means we just had to use one K-point for each of these systems to get the converged absorption energy, at least at the DFT level. And so we do that also at the QMC level. However, for the calcium on graphene system, it wasn't so straightforward. And what you'll see here is first the band structure for calcium on graphene with the hydrogens on there. And here, the thing to note is, for example, in the spin-up channel here, you have some smearing might affect the system. So you can see this line cross over the Fermi. So we're starting to maybe see a little bit of smeared electron density, a little bit of fractional occupation, which could cause some problems. However, largely, there's always the same number of electrons as you go across the different points. However, when you look at the substrate, it looks quite different. So now you have different occupancies depending on where you are. And so what that means is that you might have varying occupation of your states across the band structure. Now, that could be okay as long as they are basically mostly integer occupancies, because that's fine when you move to QMC, where we want to stick with integer numbers. So I'm showing here visually what happens is what we wanted to do is to find a grid that basically always falls as much as possible on an integer occupancy, but at the same time, a grid that's dense enough so that it gives a converged absorption energy. And so I've highlighted that in the pink crosses. So you can see on the left-hand side where there's 4 hydrogens, it basically always lands on a sort of gray circle, which means that there's always the same number of integer 109 electrons in one spin channel and 109 in the other one. Where in the other case, instead, you have cases where the crosses land on different colored circles. So that means there's a different number of electrons. However, it's fine because they are mostly integer. So that's in this last column here. There are 2 points where it isn't integer. However, it's easy enough to deal with because it just means that we make sure that the average of them is the same. So that means that in the QMC, in one of those points, there's 209 electrons, and in the other case, we'd make it 210 so that the average is still okay. And we check that by looking at the absorption energy that comes out both at the DFT level, and we see that this makes total sense. So we move on in this way. Okay, and so now this is the main result. So what you see here in the blue bars is the QMC results. And in the red, you see the PB plus D3 results. I've just referred to here as DFT, but of course it's PB plus D3. And the main take home that I want to point out is that the trend is not the same. So actually DFT would predict that the calcium on graphene system would be the most stable and would be the most promising for storing hydrogen. But actually the QMC suggests it's actually one of the weakest. They're relatively in good agreement for lithium and sodium. So that suggests that for certain kind of mechanism, the DFT is not doing too badly. But as soon as it comes to this Q-bus interaction, then the DFT is really overestimating that absorption energy. So now there's the question of, well, is it like in the gas phase cluster? Is it the case that this mechanism shouldn't be viable at all? How do we answer that? Well, what we can do is look at the physisorption structure. So using PB plus D3, we found a minimum that is a physisorption configuration of hydrogen around the calcium on graphene. And then you can see here in the middle how those orbitals look different to the one where you have the Q-bus interaction. So I'm just showing here on the side that if you use a Hubbard plus U correction on the chemisorption, you see in the brown line, that's the calcium D state, you will see the occupation of that, whether you use a low value of a Hubbard U correction or a high value of a Hubbard U correction. So what that means is you can localize that, but actually it's still there. So it doesn't seem to go away when we use a Hubbard U correction, which is interesting to note. Because it means that we can't really use a hybrid functional here, but at least with the Hubbard U correction, we can see what is the effect, and we see that that state still seems to be there at the DFT level. But then let's see what happens when we did QMC on the 2 orbitals that you see in the middle, on the 2 states. And so that's shown here in this figure, where you should look at the blue. So that's the DMC results. And you see that actually the DMC result is still much more stable than the physisorption well. So it's a a lot more stable. So it's 18 millielectron volts more stable than it would be in the physisorption law. So that sounds promising because it means even though DFT is sort of overestimating the absorption energy, the actual interaction itself might still be viable, according to the QMC. Another thing to just quickly note is that I've plotted here in green the Hubbard U correction with different corrections, so going from 1 to 6 eV, and you see that it doesn't, of course, affect the physisorption law because that should be mostly van der Waals. It should not be affected by what's near the Fermi energy, whereas the chemisorption law is strongly affected, and that again points to the idea that we really need QMC in systems like this to understand what's going on and to pinpoint the what is accurate and what is not. Okay, so I don't know how fast or slow I was, but I just want to wrap up quickly and say, okay, so QMC indicates Q-bus interaction is viable, but could be 2 weeks still for hydrogen storage in terms of the ranges that we're looking at. So for us, the interesting thing would be, though, is to look at how we can boost further towards this energy range. Now we know that maybe this mechanism can exist, maybe it can exist in a slightly different kind of material, and we're going to keep searching in that vein. I'd like to thank everyone who's involved in this work. So Angelos Michaelides was involved in the first work that was principally done with DFT, and then as well as Andrea Zen and Dario Alfe. And so the citations are there if anyone is interested. And also I'd like to thank the people on the site whose discussion was very helpful towards this work. Just to note again, QMCPACK was used for most of those QMC results that you saw. A couple of times Casino was used just for verification as well. And yeah, it's been a pleasure. Thank you.
Thank you very much, Yasmine, for a very interesting talk. Lots of interesting work there. So paper's open for questions. Is that a question, anyone?
No, not yet.
Sorry, I tend to talk very fast. That's why probably it was a bit too fast for people. But
so I have a question on the QMC side, and perhaps you did this. I was wondering if you explored the sensitivity of the binding energies and any charge transfer with different choices of trial wave function. Because you showed, Mikkel's 2010, I want to say, study, but of course that's not on graphene.
No, yeah, indeed. So yes, so we did manage to use PBE actually. I was hoping to actually use PBE plus U, but the way that PBE plus the U is implemented in quantum espresso made it very difficult. Because calcium is not a typical element that you would apply the plus U to. So in the end, we just did the test with the PBE orbital instead. And the results were basically in agreement for the QMC side. So using PBE or LDA orbitals led to the same absorption energies, I think within 2 sigma. There was agreement there. However, I think that still, it would be interesting to use quite a different approach, because for this kind of system, I would expect that perhaps PB plus LDA are too close together, let's say, in what they predict in terms of orbitals. Because you saw that with the PB plus U, even with a high value of plus U, we would still get that state, right? So it means that the orbital would still look pretty much the same. So then on the QMC side, you would expect that would not be affected so strongly. However, it would be interesting to use a completely different method where maybe it would flip how the orbitals would look.
Thank you. Anyone else have a question?
Now I have the time to formulate my question better. So, impressive work, Yasmine. I'm just curious because we are also very much interested in either graphene by itself with putting stuff on it or intercalating it between layers of graphene, or doing hydrogen storage by trying to put as many hydrogens as we can on stuff. But one thing that that at least I'm worried about is the moment you start putting larger atoms that have larger nuclei on top of graphene, you expect to see some level of deformation happen. especially when you start having to bind larger things and having charge transfer starting to matter. And the problem is that sometimes those will affect significantly whatever property, especially if it's storage or charge transfer. So how are you dealing with that? Did you try to do relaxations? I know, and additionally, when you show differences that are that large between DFT and QMC, I tend to not trust so much, or at least I don't have a reason to trust DFT forces in that case. So how are you planning to answer that or to deal with that?
So I think that's an excellent point. And indeed, we're also thinking about what, how does this tie in with the sort of real world situation, right? And the thing about the deformation is, so if I understand at least part of your question, we are actually interested to maybe exploit that deformation, because one of the things is that I'm just showing metal atoms that have been optimized with PB plus D3 just sitting on top of this graphene. But in reality, you'd think that experimenters would like these to be anchored better. So actually there, I think, if anything, we need to look at introducing perhaps more defects to move towards reality, let's say, and to see how these decorators could be, first of all, anchored, and then secondly, how would that affect their absorption of hydrogen? But so if I understood your question, you're also saying at the same time, you wouldn't trust the DFT forces, is that right?
Yes.
Just well,
based on the fact that when you show, for example, that for lithium and for sodium, you get a good matching between DMC and DFT. In that case, I would say, yes, that's forces might be also fine if the energies are fine. But when you have such a huge discrepancies, for example, for the calcium one, I would say if you are so wrong in the energy, how could the force be correct?
Yeah. That's a really good point. I think that this is one of those situations where we could either sort of fish for a functional that matches a little bit the energetics of QMC better, and then sort of benchmark essentially for a functional that perhaps matches that better, and then get the forces from there, or even skip that and go straight to machine learning. But either way, I think you're right that in that case we would need to have essentially more information from QMC probably, to build up the energetics, and then from that deducing what method could be good for the forces. I think it's probably going to be the most realistic way to do it, to my mind.
I would like then just to point that there's this method called Hessian method for force relaxation, or that's it's just like because Jaren is developing. We had he had a tutorial about it. If you have the chance to look at it, he developed methods to be able to use to do some level of relaxation. You have enough symmetry points here to be able to run it, and it should not even cost you that much for this type of problems, I think.
Oh, thank you for that suggestion. I will definitely be trying to catch up with all the things I've missed. Thank you.